So they get these binary interaction parameters by plotting the equations of Wilson, for example, so that it will then match the VLE data of the experiment. So I will let's see so they can calculate this. You can see so they can calculate the we have the molar flow rates in the liquids. They have these activity coefficients. They have this pressure of the component at saturated point, which they can then use the Antoine equations to calculate this number. And then you can see these two are the Wilson equations. And then in these Wilson equations, they have these interaction parameters. Lambda 1, 2 means lambda of component 1 and component 2. And then this lambda 2, 1, lambda component 2 and component 1. Okay. And then they have another expression. And then they will then do all of these 6 equations, and then they will then try to fit the VLE. Let me see if I can get something from you. Why I select Wilson? Because this is one of the easiest ones. Yeah, this is the one of the easiest because it was also one of the oldest thermodynamic model people have used so far, and this is also one of the easiest ones, obviously. So that then we can follow how it is being calculated. At least we can have a feeling. So so I have with me here the methyl cyclohexane and ethanol. Yeah, and then the Antoine equations for the ethanol, we have these equations of Antoine equations, yeah, depending on the source of data. I have 2 sources of data at a time, so we have this P set as the in kilopascal, while for the methyl cyclohexane somehow I have the data for the unit in torr. So we have the ABC of the ethanol, and then ABC for the methyl cyclohexane, and then at these conditions. So at this condition, 380 torr, 55 degrees C, I have this vapor liquid equilibrium data. So we do the experiment in the lab. We specify the pressure, we control the temperature, and then we measure how much methyl cyclohexane in the liquid, and then how much ethanol in liquid, how much methyl cyclohexane in the gas, yeah, as in the mass balance, and then how much is then the methyl cyclohexane in the gas. So these two they can measure. They know how much both components they put in, so they can then calculate this accordingly. So at this temperature, they will then calculate the P1 saturated, P2 saturated based on this formula, and then they can then calculate because they know the Y, right? They know the Y, they know the P total, which is this, they know the P saturated already calculated, and then they can calculate the gamma, the activity coefficients. You can calculate the activity coefficients for 1 and 2, and then you have seen these equations, right? From that article. Where's the article? Yeah. From this article.
Oh, article.
These equations. So you just play around with the equations, and then we try to find. I have 2 ways now: the blue ways and then the yellow ways. So let's just do the blue ways. So we need to find. So we just guess this A12 and then lambda 1 2 and lambda 2 1. We just use this as a guess number. You can use any number, and then you plug it in. Yeah, use this. This is then the equations of this number, this part, and then this is then the equations of this one. So we know that when we plug in this gamma 1 2 and gamma 2 1, we know the x1, we know the x2, we know the gamma 1, yeah, and then the calculations of this left hand side of the equation, it should be equals to 0. So we need to find gamma 1 2 and then lambda 1 2 and lambda 2 1 in such a way that this left hand side equation equals to 0, and similarly this has to be equals to 0, and then that's one way. So in this case, if I use this, you can use Google search, you can use Goalseek or Solver to do so, which we can then do in the other topic, yeah. So we search these two number in such a way that these two are 0. So this is then the parameters, the corresponding parameters for that for this particular equations. And then on the if we can also work around these two equations and then make it like this one. And then so we need to make sure that this has to be equals to that number. So we just need, in this case, we just need to guess only one, yeah. For example, lambda 1 2, and then we guess lambda 1 2, and then we calculate the lambda 2 1 in such a way that the difference between them, the difference between gamma 2 1 and then this has to be equals to 0, like in this case. So using equation blue and then using equations yellow, we can reach more or less the same number. So this is what we call as the binary interaction parameters between the ethanol and methyl cyclohexane in this particular thermodynamic model, which is the Wilson model, yeah. And then based on this number, we can then calculate, yeah, we can make a plot, yeah, 55 degrees C. We can make a plot, so we just yeah, vary the mole fractions in the liquid. We calculate the gamma 1 and gamma 2, yeah, and then using these equations, obviously, and then we get this gamma 1 and gamma 2. We calculate the ln, we get the gamma 1 and gamma 2, and then we can then calculate the P total, this using these equations, the P total, and then we can then calculate how much is then the liquid, sorry, the mole fractions of this component 1, the methyl cyclohexane, in the vapor. Okay, and then we plot, this. Yeah. So we plot this, the x. Why is taking so long? Go on. Yeah, and then we plot this x1, the x1, and then against the calculated p, which is this p, and then we make a plot, and then this plot is the one that we are going to compare with the other experimental data if we have them. Yeah, for now in this particular example, we only use this data, this set of data, only one data point to get this binary interaction parameter, and then in such a way, using the same binary parameters, we can make this plot. So the next step is then to find the actual experimental data, so that we can see whether our plot matches the data or not. Okay, so this is about the this is Van Laar equations. So Van Laar equation, it has a different one. Sorry, it's also Wilson coefficients. But in any case, when we go back to the oh, I haven't opened anything. So I don't know if you know, this is what I want to share with you as well. The So this is then the book from Truton, that analysis, synthesis, and design of chemical processes. So in the appendix B, they have like a 15 chemical processes that you can try on your own. I often do the dimethyl ether production as a case study for any simulation. I don't know if you would like to do that as well. Yeah, for me it's I use this typically because this is then the simplest process compared to the other 15. So compared to the 14. So that in that sense it will be easier to explain things using this very simple process, and then as we go along, then we can add up some information. So we have only like methanol, DME, and water. So if you go, if you have any questions, just ask. Yeah. Are we clear on these binary interaction parameters? I think when we do examples, it will be clear, because the selections of thermodynamic models will highly influence the accuracy of the results, especially on the vapor liquid equilibrium. Come on.
So, Doctor, I just like to be clear
Yeah.
about so different fluid package would use different equations, say Wilson or Van Laar, or even more complex equation to plot the VLE diagram,
Yeah.
and trying to simulate flashing and stuff like that.
Yeah.
Is it true?
Yes.
Am I understanding this right?
Yeah. Your
Okay.
understanding is perfect. Thermodynamic models. I've seen once in Wikipedia. It's quite okay. I mean, it's quite comprehensive. But let's see whether we can find it again. Say for example, NaTl is one good one, and then you are, I think, familiar with, I don't know, PSRK maybe. There's no Peng Robinson here. So you know the equations of state. Maybe this one. Come on. Yeah, this one. So equations of state is then the one type of thermodynamic model. So we have equations of state, which is based on the PV nRT, and then expand this PV nRT. So the first guy is then this is the ideal gas law, the PV nRT. Yeah, the PV nRT. Where's that? PV nRT. And then some other guy like this van der Waals says, well, we need to account for volume. So because one molecules like methane and hydrogen, they have different sizes, right? So it's very easy to imagine that different molecules have different sizes. So if one molecule has a bigger one, so it may have a different interaction compared to the smaller molecules. So they add this. They add this one, the correction for the volume. Yeah, so they have this A and B, which they calculate the A and B based on the temperature critical and pressure critical of the components. So depending on the critical pressure and temperature of the components, they calculate the A and B accordingly, and then they can do this use these equations to calculate how much is then the molar volume. Why molar volume is very important? Because in the end, you want to size the equipment, right? You want to know how big is then the size of a pipe, or how big is then the size of a vessel. So to know the size of something, that means we need to know the density of that thing, or we need to know the volume of that thing. Yeah. So this mass, density, and volume, they are related to each other. So if you can then use these equations to calculate for you. So if I need to pump or compress or let a fluid flow from at a certain temperature and at a certain pressure. So what is then the size of the pipe, for example, and then I need to know what is then the volume of that fluid. So you can use these equations, you can calculate the volume, and then you know how big the pipe or how big the vessel is. And then new data comes in, new data came in, and then they will then, because it was in this 19th century, the new data came in, and then they see, okay, well, this equations of state is not doesn't fit anymore to the new data, and then they will then develop this further with Redlich-Kwong equations of state. We can see you can see this van der Waals, very simple, and then people then, so these two people, they make it even more complicated. So they still have the correction for the volume, but they have another corrections over here, and then some other guy came, this one, SRK, so they make another corrections over here. The goal is the same, to calculate the size or the volume of the molecules. And then you have the Speng-Robinson equations. So you have also the quadratic form of the volume, and then you have this PSRV, and so on and so forth. So in each of these equations of state, you can see there are constants that they need to calculate first before they can utilize the model. You can see that, and then that is about the equations of state. The NRTL, for example, is also another thermodynamic model using the activity coefficients. So it's more complicated than the equations of state. It is used more on like because these equations of state, it was primarily developed to approximate the behavior of gases. Okay, while this the activity coefficients, it was primarily developed to estimate the behavior of like liquid mixture. It's more like if you find like a non-polar or like non-ideal mixtures. So we prefer to use, or these models that are based on activity coefficients, they can be how do you call it? They can approximate the situation much better compared to the equation of state. You can see these equations. So compared to this guy, for example, compared to this guy, you can see that this equation is more complicated. See, in the NRTL, we need to find this, which is the dimensionless interaction parameters, and then in the PSRK, and then in the PSRK, we also need to find, they have this PSRK based on this SRK. It's also part of the equation of state, and then it has its mixing rule. So if they have different compositions like I and J and so on and so forth, they can do this. So we can calculate the A and then the B, and then to put that A and B in over here, if we have mixtures, and this is then how we calculate the A and B of the mixture. You can go through this, and then you can read the advantages or disadvantages of the of each of the thermodynamic model. So one good book that I recommend you to read is then the process simulation. Thermodynamic process simulation. This one. So this is a good book for you to read. Chemical thermodynamics for process simulation. So in it, they explained everything, and then try this, and then if there's anything that you don't understand, and then we can also discuss it in this session. So so far based on this very rough explanation on what thermodynamic model is, do you have any, is it a bit clearer now, or did I need to do I need to explain more? because if I need to explain more, that means yeah, we will then change this title of the course into thermodynamic course rather than the process simulation course. Which I don't mind, yeah, but then we can go through this again, or maybe we can just restart your undergraduate teaching. Is it clear or a little bit clear?
Yes, sir.
Or very much
A
clear?
little bit clearer.
A little bit, yeah. So
Very
we'll
much.
see through an example. Yeah, it will be easier through an example. So so we had this methanol water and dimethyl ether. Yeah. I miss. No, I'm not too fast here. Do you know how to open and then add the components? Yeah.
Yes, yes.
Okay.
Yes, sir.
Okay. So it's easy, and then we will focus more now at this for tonight. We'll focus more on playing around with the fluid package or the thermodynamic model. So we'll do yeah, we will just select some of them, right? So we will select I don't know, which one do you want? Anything, any preference? So maybe we use NaCl. And then we could also add another one. So this one, this then the NaCl that we just how do you call it, selected. Sorry, that one. So we just selected the NaCl. It says here vapor model using the ideal, that PV and NAT stuff, and then the density is then using the Costalt. So you can Google yourself or go through what it means. Yeah, it can mean anything. So Redlich Kwong, Virial, Peng, Robinson, SRK, so Redlich Kwong, the one that I just showed you. The binary coefficients of this. So by default, yeah, by default, let's just rename this so that it's easier. I'll just rename this to NaCl so that we know. So this NaCl fluid package is using NaCl, yeah. So that's as easy as it is. So we go click edit, to just double click it here. So if we go to the binary coefficients tab, because it's using NaCl, so you can see, so the Aij of interactions, there is by default, it has these interaction parameters between the water and methanol, and then methanol and water for this NaCl, and then the Bi, but there is nothing for the other components. Yeah, there is nothing. So that means we have to either find how do you call it, an experimental data, and then try to regress it the way that I just showed you using that Wilson equation, or in this case we could also do we can then estimate using the UNIFAC method. Yeah, so this UNIFAC method is basically, it estimates, yeah, it estimates the binary interaction parameters by using the functional groups. So methanol, you have the C3 and then CH3 and then OH, right? So these two functional groups, and then the water has H2O, and then dimethyl ether, it has ether, and then it has methyl. So you can UNIFAC. Somebody should have a table. This one. See, it has all of this CH3, CH2, CHC, and so on and so forth. It has these numbers. Yeah. So depending on the components that we are dealing with, it will then calculate. It will use these numbers. It will use these numbers to calculate for us the binary interaction parameters. When there is more than two components, yeah. So the so that means this binary, the name is binary, so if you have like three, because now we have three components, it will then calculate, we need to know the interactions between water methanol, but also dimethyl ether and methanol, water and dimethyl ether, methanol and dimethyl ether, and then dimethyl ether and water. Yeah. So if you click on this later on, if you click on this, it will then estimate for us the missing binary interaction parameters. Okay. So I will leave it as it is because I will show you later on. And then there's the Bij. There's also another term which obviously that this NRTL is not using it. It's all zero. This one is also it has something there. Okay. So I will put it here, but then I will add another one. So we also use NRTL. Yeah, but then I will rename this NRTL modified. Okay, so this one we leave it as it is, but then this NRTL, the modified one, double click on this one. The modified NRTL is the one that, for example, we will then estimate the missing parameters, and then we will see what the effect is. Yeah, so I'll just click. So see, if you compare it with here, this one, this guy, so it's nothing. 610 minus 48, that was then the default number between this water and methanol. But then if you go to the NRTL, this is the same 610 minus 48, but then it will then calculate for us already the missing ones. Because I click here unknowns only, sorry, I just click here unknown only, so only the unknowns that are being calculated by the UNIVAC estimations. Hij still 0, alpha it's also the same number. So basically I think in these two terms are not used by the NRTL. And then another one we could also select. What do you want to select? Any volunteer? Wilson maybe, because we'll be talking about Wilson. So I will say this then Wilson. This then Wilson. We'll do Wilson, and then we will do another one Wilson modified as well, so that we can then compare it. This is then Wilson modified. Yeah, so in this Wilson modified, we can also do the same. You can see the activity coefficients between Wilson and then the NRTL, they are different, right? So 610 and then minus 52. This is 620, and the 610 and then minus 48. So a bit different. So depending on, I think you know it already by now. So depending on the equations that we use to regress the data, hence we get the differences. So we only estimate. So when we click estimates, so it will then estimate the other missing interaction parameters, and then we can. Do you want to add more or no? I think this is enough, yeah. Or add one more, like Peng Robinson or something, because kids not recommended. So it has this when we use. So Peng Robinson cannot do or cannot estimate this guy, the dimethyl ether. Cancel uniquark. Yeah, and then we add another one, also uniquark. Yeah, just to give a flavor. So this is then uniquark. And then this is then uniquark modified, and then we will then do this uniquark modified. See, the equation, the binary interaction parameters are different because obviously they all three use different equations to get to match the data, so to say. Okay. Until here, any other questions? Otherwise, we go to the simulation, and then okay. So we go to the simulation. So now we have like 6 thermodynamic models that we can use. Yeah. So okay, so how we do this? So this is what we call like model palettes. So in this model palette, they have everything. So you can all is it will then show you all. You will get overwhelmed. Dynamics and controls is about dynamics and control only. External model is external model where HYSYS can talk to like this wellhead, this virtual stream. I don't know. There's also Olga, I guess. Cap open, cap open. So Olga. Yeah, Aspen custom molder is there. And then add heat transfer, about heat exchanger. Manipulator is about process calculator, recycle, adjuster, piping, pressure changes is about pump, compressors, valves, reactors, separator, separator. So you know this. So we'll see. Yeah, we'll just have like a stream. Click on this and then click again on the environment, I would say, and then we do we'll just not add another one. So we have like a vessel like this, separator vessel, and then I want to make it like smaller. I can just scroll in and out to make it to change the size. And then if I want to make a connections, there are many ways to make a connections. Number one is that just press Control and then hover your cursor to the stream, so you can see out, and you can just drag it to the right, and then this is then connected, and then you will see that this stream number one is already connected as the inlet. And then you can also do like just type in here vapor, and you'll get your vapor. And then you could also liquid, so you get your liquid. Okay, so now in this case we can have all of our models there, yeah, to calculate this unit particularly. So we will just close this, we'll come back to that later. So stream number one, so by default it will then use the NRTL, yeah, as you see this, because that was then the first model that we have selected. So stream number one, so we want to say for example this is the thick compositions. I don't know, maybe we'll see like I don't know, maybe 0.4, and then this is 0.4, this is 0.2 for example, and more fractions. Yeah, you can change to mass fractions, liquids, mole flow, mass flow, whatever. So as long as you know what to do, 0.4, 0.4, 0.2, you can just do whatever you want. And then if they're not the same, for example, if it's more than one, for example, when you click OK, and then it will then be normalized automatically. Otherwise, you can just click normalize and then click OK. Yeah, it's either way it's okay. So we get the compositions. So as you know it. So once we know the compositions, that means we need to know two more conditions, either the vapor or the temperature or the pressure, so that they will then you can calculate what the condition is, as we understood it last time. So our flow is still 1 kilogram an hour to make it simpler. Now pressure, assume it's at like atmospheric, yeah, atmospheric one, and then either space, or you can just scroll this down, 1 atm, 1 atm, and then temperature, assume it like 30 degrees C. So we have in this 30 degrees C 1 atmospheric. If we use this NRTL over here, we'll have vapor phase of 6%. Yeah, vapor phase of 6%. So that 6% will go up as a vapor, and then the rest, the 94, 93, 93% will go as in the liquid. Okay, so they have this. So you have like a 1 kilogram. Let's put it like 1,000, so it's easy. So 1,000 kilograms an hour coming in. So 98 kilogram will go up. 901 will go down. So that's if we use this NRTL. Okay, so this is then the original NRTL, yeah, without any estimation of the binary parameters using the UNIVAC. But if we change this to the NRTL modified, you can see this. Yeah, I will then maybe I don't know, maybe some of you will take the picture of this. Just remember, yeah. So 658, yeah, 6.58. So we change it. because this 658, yeah, it will then define the volume. So define the volume, how much compositions, yeah, how much is then the water goes to the top, the metal ether go to the top, and then the metal ether go to the liquids, and so on and so forth. So we know that the majority of the metal ether goes to the top, and then only 15% of it goes to the bottom. Okay, sorry, only 15%. There's a 15% of dimetal ether in the bottom, and then 87% of the dimetal ether in the top. So that's if we use the NaTl. Okay, I'll just yeah. Can anybody of you like take a picture or something, and then we will discuss, yeah, on this NaTl. So and then we do the NaTl modified. So you can see we change this NaTl to NaTl modified. We use this unifac binary interaction parameters. It will then say it's not 6% that goes to the top, it's 15% that goes to the top. Right? So 6 to 15% is a huge difference. It's a double. And then you will see the compositions. So we have 86%. It was, I don't remember how much was it of the metal ether in the top, and also some. But these numbers seems to be not so much different compared to the difference in the how much vapor and liquid is being separated here. Okay. The same goes if we do the uniquark. Uniquark gives 8%, and then the uniquark modified gives 15%, and then the Wilson nothing. So according to Wilson, everything is liquid, yeah, no gas. But then if we use the Wilson modified, 15% is then the one that goes to the vapor phase. So we could see, yeah, if we use this the binary interaction parameters estimated by the unifac, they like, yeah, 15%. It's 15%, and this also 15%. So it's more like so this it shows that how strong this binary interaction parameters affecting the how much is then that one, how much component goes in the vapor and then in the liquid. So while the original model, it's they differ quite a lot, yeah. So that's how we then one is then how we see the effect of these binary interaction parameters, and also the selection of the thermodynamic model to the results that we have. And then number two is that once we know it's number two, is then we need to find, we can actually we are able to fine tune the thermodynamic model in such a way that it will then mimic the data if we have it. Say for example your plan says, well, at these situations or at these conditions I have like some 1000 for example, I have like I don't know how much 1000, and then it says there are some vapor because the pipe is then vibrating, yeah. And then that means not all of the liquids is not all of the feed comes out of liquid, some of it comes out of the vapor. So that means, you know, when you use this Wilson, it will not be correct, yeah. So we need to find a different one, either NaTl in this case, or uniquark, or you have to like use the modified one. So in that sense, you can go deeper. You can then measure how much is then the liquid coming out. Sorry, how much is then this one, you know, this one you need to measure, and then the difference between them is then the vapor, right? So when you use this vapor, and then you know how much is then the vapor, you calculate that, and then when you use this, for example, the uniquark, it says 8%. But then if you use this, you estimate the binary interaction parameter, it says 15%. So how much is then this difference compared to the ones that we estimate? If this is somewhere like 14%, 15%, then we know then for sure that the modified one is then the one that we are going to select. Yeah, and then the next case is then if you can get some compositions analysis over here. and the liquid, and then you can compare. Okay, so with this for example, uniquely modified, the composition of liquid phase is about this number, and then when you do your experiments, you take a sample, go to the lab, measure the compositions, and then if you get the numbers more or less like this, and then you can be sure that this is then the correct model. If not, then you can then fine-tune, see what happens. This is also more or less the same. This one also it's also more or less the same. So basically the compositions is more or less the same, it's just that the amount is different. This is slightly different. So you can see which one fits your data best, and then you can then be sure, okay, this is then the correct thermodynamic model then I can use to model my plant further in this particular case. The same goes, for example, you can see this is then related to that one. There's a question. Oh, no question. Now, do you have any question?
No.
Up until this point, is it clear on the effect of these binary interaction parameters and then the thermodynamic model of fluid package that we are selecting, and then how we what information can we get from this selection, right? And which we need to use this information so that we can then mimic what is happening in the plant. Yeah. Any other questions? No question. So if there's no questions, and then we can go ahead. Yeah, we have 10 more minutes. View. Where's the view? Rotate. To the right. Oh, clear. Very good. If it's clear, then it's good. So we have methanol. Yeah. So this process is then, I think I've explained this process last week. I don't think I need to explain this again. Yeah. It's only very simple. We need to have 2 moles of methanol, dehydrate that to make water, and then the DME being the lightest, it will then being separated in here in this first column, the DME column, and then the water and then the unreacted methanol goes to the second column, where the methanol is then taken at the top, recycled back, and then the water goes away. Okay, very simple. So methanol stream number 1. So we'll do this. Sorry, methanol stream number 1. Okay. So stream number 1, 25 degrees C, 1 bar, and then we have this moles and we have this flow. So the easiest way, because we have already the flow rates, so we will just key in the flow rate. Yeah, and then temperature, pressure, and vapor fraction. So which one do you prefer to key in? Yeah, because we cannot key in all of these 3. I think you still understand why we cannot do so. If not, just let me know. Which one do you prefer?
Maybe it's just vapor fraction and pressure.
Vapor fraction and pressure. If we specify vapor fraction and pressure, what does it mean then?
They will calculate the temperature.
Okay, what does it mean then? I mean that if you specify 0, what is that thingy? So if you say you specify pressure and you specify vapor fraction, so specify vapor fraction equals to 0. So what does it mean? This vapor fraction 0, and then we specify a pressure. That means, is it like because if we specify vapor fraction 0, that means it's a liquid, yeah. Pressure is 1. But this liquid, will it be like a saturated liquid or subcooled liquid?
Saturated liquid.
It will be saturated liquid, exactly. It will be saturated liquid. If you put this 1, that means it could be like saturated vapor, or it is superheated vapor. Yeah, so in this case, if we put this one, that means it will be the saturated vapor. So that is then the impacts, and then I will just show you what happens. Yeah, I'm not going to say anything. A minute. Yeah, composition is remember this number. Yeah, 259.7, 2.5. 259.7 and 2.5. 2.5. 2.5. So we will use basis, change it to basis because we are so lazy. Mole flow. This is 0. And this is 259.7. This is 2.5. Yeah, I think so. Oh, this one I will answer later. And then click OK. Click OK. What the hell? Yeah, I know. And then we remove this because we have specified the flow rate. So that means we need to know. We don't need to specify any flow rate over here. Delete. Hey, sorry, I deleted that. 259.7, 2.5 mole flow. Okay, so flow rate is there, and then this 1 bar, 1 atm, 1 bar, say 1 bar, 100 kilopascal, and then you say unknown flow rate. Oh, okay. And then you say you know what just happened? Yeah, we had different. I mean, we had the error in the inputs, and then we'll then calculate. The calculation will stop automatically, and then when we key in the correct input, it won't start automatically. We have to click on the active. Yeah, that's how what just happened. So now let's see. So if we put this 25, sorry, 25 1 atm. So 25 on atm. What in the world is happening? 25 and 1 atm. It's all liquid phase. This is 0, but this is then we don't know whether this is then saturated liquid or subcooled. Yeah, so if we delete this like you suggested, and then you put this 0, so that we want to have like saturated liquid, it will then calculate for us what is then the corresponding temperature, which is 64 degrees C. Right? So 64 degrees C at 1 bar is then the saturated liquid situation. So if the temperature drops below 64.28, that means everything will be subcooled. Yeah. So our situation at 25 degrees C, 25 degrees C is then the subcool. So if we follow your advice on okay, we select the pressure and then we select the vapor fractions becomes 0, you will get temperature of 64 degrees C, which is then the saturated liquid. So it doesn't match with the data that we have, because the data that we have, we will need 25 degrees C and 1 bar. So corresponding to that is then the subcooled liquid. Okay, the 8.37 tons an hour, it is being calculated automatically, 8.37 tons an hour. Okay, the question is, in most cases in the plant, do we really need to experimenting it, or we can just find it on literature to compare our data with the model and software? So what do you think? Does the book know your plant?
Literature, maybe.
Yeah, I mean, literature is the book, right? I mean, that literature, does it know your plant? Huh? Come on, 3 more minutes to answer. Does it know your plants, this book, literature, this
But
pattern?
what if the plant does not exist yet?
If the plant doesn't exist yet, yes, you need to find literature. But if you have your plant, well, the best thing for you to do is then to do the analysis. okay, because how do you call it, we don't know what the exact compositions, right? I mean, to get all of this data, I mean, to get how much is then the volume, how much is then density, and so on and so forth, we need to know exactly how much is then the compositions. But then these compositions, how are we going to get this?
From real data.
From the real data. So there is no literature saying, well, your stream is 259.7 kilomole per hour and 2.5 kilomole per hour of water. There's no such literature for that. But we do know we need these compositions, and then we can then estimate the other properties. Okay. It's best to define temperature, or it depends on the case. Why it's depend on the case? Because put it here. It's to so that you don't see me. So in this case, it has these three data, these three informations, yeah. Because then your operator comes to you, sir, I have measured this, so temperature is 25 degrees C, pressure is 1 bar, and then the vapor fraction is 0. It says it's all fully liquid, right? And then now your task is then to put these three informations into the simulation software. So what do you think you need to do, right? So you could try, if you don't know, you could just try like what we just did. So put this in, so put this in, and then you don't know, you say, well, it's a full it says liquid, liquid is, then that means this is then 0, and then it will calculate for you 64 degrees C. But then you don't think it will be that hot, right? Temperature 64 degrees C is something that's quite hot. Okay, you know from any lecture or from this lecture that this is then the saturated liquid. So well, it cannot be this case, so it could be this subcooled liquid, and then you can go measure yourself, you get this 30 degrees C, for example. Or if you also don't know, you could play around, yeah. Sorry. So you could also play around. So this is 0, and then you don't know what the pressure is, but you know what the temperature is, right? So this says it is saturated liquid at 25 degrees C, so the corresponding pressure is 16 kilopascal, which is vacuum, and you know that it cannot be vacuum, right? So if it cannot be vacuum, and it cannot be like 65 degrees C, so well, it's all in saturated liquid and saturated vapor, so it has to be like subcooled or superheated vapor. So it cannot be like superheated vapor because it's a liquid, right? So it has to be like a subcooled. So now you know. So that means this guy, I cannot specify it. I cannot specify this guy, so I need to specify the temperature and the pressure. Hence I get this. So this number fits to the data, this number also fits to the data, and then you can be happy. So I will see you again next week. Okay, it's 10:31.
Right.
Yeah,
Thank you, sir.
make a list of your questions. Yeah, make a list of your questions, so then by next week we can have a questions. You can try this. I will just save this. I'll save this. Yeah, 1 hour is very short. Yeah.
Exactly.
DME. Okay, DME. 1 hour very short, but then so you cannot. I mean, in this whole learning, like also in UTP, when you were a student, you cannot really depend. You cannot depend completely 100% to your lecturers, because the time that you have with him or her is very limited. The same goes in this exercise. So we really need to invest a little bit more, or a little bit more of our time to like self-study. Yeah, and then when you have when you meet your lecturers, and then you can then discuss things that you don't understand or you don't quite understand with him or her, and then you can have a better view or better understanding of how things are going. Okay, so thank you.
Thank you, sir.
Yeah, make a list of questions and then do this. I think you have this, right? This appendix, Tuton appendix B. And then try to do it yourself, and then if you can do it, yeah, I mean, I think you can do it, and then let me know, and then okay, so
Right.
bye bye.
All right. Thank you, doctor.
Right.
See you
Bye.
next
Thank you.
Yeah,
week.
thank you.